So in this session, we are going to discuss about various approaches of gastrointestinal drug delivery system. So, what is gastrointestinal drug delivery system? So, gastrointestinal drug delivery system is an part of a control release drug delivery system, and you can say that it is a site-specific drug delivery system, where the drug it will release or deliver from the dosage form into a particular site. Okay, so here the drug it will release from its dosage form in the stomach. Okay, so it is a site specific drug delivery system mainly in the stomach. Okay, and it is a part of an control release drug delivery system. Now, what are the various approaches or method to prepare that gastrointestinal drug delivery systems? So there are various approaches are there, like floating GRDDS, uh, high density or sinking systems, then biodesive or mucoadhesive GRDDS, then inflatable gastrointestinal delivery system, and swallowable GRDDS. So these are the various approaches or method how we'll uh, prepare that or how we'll manufacture that gastrointestinal drug delivery system. Okay, so coming to that first method, it is called that floating drug delivery system or floating type gastroretentive drug delivery system. So this floating drug delivery system have and bulk density that lower than the gastric fluid. I think you have clearly you can see in the picture that how a dosage form in the form of a tablet, it's floating. Okay, it's get float in the gastric fluid. Okay, it's buoyant in the stomach for a prolonged period of time without affecting the gastric emptying time. Means the gastric emptying time, if you're taking the food, okay, or water, so it will not get hamper or affect the gastric emptying time. Okay, it will not affect the gastric emptying time with a normal or in the normal gastric emptying time, it will retain in the stomach for a long time. So how it will retain? It will just float or it will buoyant in that gastric fluid. Okay, for long time, and within this long duration of time, the drug it will release slowly from the dosage form. Okay, from the dosage form slowly it will get delivered. The drug will be delivered or released in a controlled manner. Okay, so while the system is floating on the gastric content, the drug slowly release at a desired rate, okay, from the system or from the dosage form. So there is an equation is there. Here it is an F, it is written as an buoyancy minus gravity. We can write as an df minus ds into g into v. So F is an total vertical force, df is an fluid density, ds is an object density, means the dosage form what is density it is, v is the volume, and g is the acceleration due to the gravity. Okay, so the fluid density mean that gastric fluid density, object density you know that is in that dosage form density. So if we'll calculate that one, we can find out the vertical force. So how the, if the you can see the df the fluid density if it is more and the object density is in less, so always the object density it should be less, then the vertical force it should more. So you can see that if the df is more, automatically the f value will increase, the vertical force will increase. When the vertical force will increase, the vertically the dosage form or that drug delivery system it will get float, it will retain in that vertical. Okay, or you can say that it retain in the surface or in that gastric fluid, it will retaining. Okay, retaining in the gastric fluid, or you can say the float in the gastric fluid for prolonged period of time. Okay, so f is equal to d small f minus d small s into g into v. Now there are various methods are there how you can prepare that floating system. So the dosage form or that drug delivery system, it will float on the gastric fluid. So that floating, we can make it in a different method. Okay, we can make a system, it is called then effervescent or gas generating system. We can go for any non-effervescent system. So it is an first one is an effervescent system. Okay, where there is a release of carbon dioxide. You know that effervescent drug delivery system or effervescent tablet. Okay, so there is a release of carbon dioxide. Okay, so there is an effervescent components are there, mainly the sodium bicarbonate, citric acid or tartaric acid. So these are the main components of effervescence. Okay, so with the use of sodium bicarbonate, citric acid and tartaric acid, we can make an effervescent system where the carbon dioxide will get released. Okay, so the floatability ability of that floating system or ability of that dosage form, okay, it will mainly generated the gas bubbles. Okay, so the floatability of that system, it can be achieved by generation of the gas bubbles, or you can say generation of or release of carbon dioxide. Okay, so it is prepared by using soluble polymers. The polymers normally hydrophilic polymer which will get swelled in presence of the gastric fluid. Example like chitosan you can say. Okay, it is a polysaccharide, hydrophilic, so which will get swelled in presence of the gastric fluid. It is an hydrophilic polymer. Or it can also be prepared within chamber containing a liquid that converted to gas in body temperature. Okay, so it can be a chamber, like suppose in closed chamber. Okay, it is a closed chamber, it is having some particular substance. Okay, which substance, like an ether, suppose any substance which will get evaporated or which will converted to gas in presence of the body temperature. Okay, in it will gasify, or you can say it will get volatile or converted to gas in body temperature. So that closed system, suppose that is completely closed system, when it will go to the stomach, then the closed system which is containing that particular substance which is converted to gas in presence in body temperature, so that will convert it to an gas. Okay, mainly the release of an carbon dioxide. Okay, release of carbon dioxide or an particular gas which will uh, liquid which will convert it to gas in a body temperature. Okay, so now that closed system, whenever it will go to the stomach, it will convert it to gas in body temperature, then it will get float. Okay, it will get float in the gastric fluid. Okay, now these are one of the system which is in called as a chamber system. Okay, containing a liquid that gasify in body temperature. Or a particular system which is having that effervescent components. Okay, that components, whenever it will come in contact with the gastric fluid, there is a release of carbon dioxide. Okay, means ultimately that is an uh, release of an gas. Okay, so you can see that in that diagram, that there is an one system, or you can say one tablet or a particular system which is having a semi permeable membrane, and inside the semi permeable membrane there is an drug chamber is there, as well as an effervescent layer is there. Okay, so through the semi permeable membrane, the gastric fluid, it will enter into the system and it will come in contact with the effervescent component. So whenever the gastric fluid will come in contact with an effervescent components, it will release carbon dioxide. So when there is a release of carbon dioxide, you can see that in the diagram, in that second diagram. So if there is a release of carbon dioxide, you can see that particular system, it will be little bit increased. Okay, because of that carbon dioxide, there is a gas will be there inside, and because of that, it will get float in the gastric fluid. Okay, so coming to the next one, it's called that non-effervescent. Okay, so non-effervescent system, we can classify it, or we can divide into various subtypes. Okay, like colloidal gas barrier system, hollow microsphere or microballoons, and then alginate beds and microporous membrane system. Okay, so what is called the non-effervescent system? Why? Because there will be no release of carbon dioxide, or you can say there will be no use of effervescent components. Okay, there will be no use of effervescent components. As in the first one, there is a use of that effervescent components like sodium bicarbonate, citric acid or tartaric acid. There is a no use of effervescent components. Okay, so that's why it is called as a non-effervescent system. Okay, so coming to the first one, it's called the colloidal gel barrier system. So colloidal gel barrier system, definitely there will be one hydrophilic polymer will be there. Hydrophilic polymer which will form in gel form, which will form and gel, or you can say that the polymer it will get swelled in presence of the gastric fluid. Okay, so those system normally it will use any gel forming, or you can say and swellable hydrocolloids. Okay, even example like HPMC is there, or chitosan also there. So carbomar also there. So these are the various examples of those particular polymers. Which polymer? The polymer which will get swell or form gel. So gel forming polymer or swellable hydrocolloids. Okay, now this type of system it consists in embedding drug powder pellets in gel forming hydrocolloids. Now the polymer and the drug, they will combinedly mix. The drug it will be completely mixed or directly inserted into that polymeric system. Okay, now when the dosage form it will be taken, and the dosage form it will come in contact with the gastric fluid, then it will get swell, the system will get swell. So when the system will get swell, ultimately the air entrap it will attain. Okay, the air entrapment is there. Okay, so because of that the bulk density will be less than 1. Okay, or you can say the bulk density it less than the gastric fluid. Okay, because of that it will get float, as well as because of the swelling system it will retain in the stomach, means it will not get exit from the pyloric sphincter. Okay, so there is an use of some polymer which will get swell. So whenever there will be any system, suppose a small system, same like the previous one. Okay, same like the previous one, you can see that the system will get swell. How it will get swell? Because there is a generation of carbon dioxide, the gas will be generated inside, so that the system will get swell. Okay, then it will get float. Okay, same like suppose, and suppose a balloon is there, when we'll inserted air in that, so definitely it will not sink in the water, it will always try to float in the water. Okay, so same here. So whenever a system it will get swelled, when it will get swell, then definitely the air it will be present inside that particular system, the air entrapment is there, and because of that the total system density it will decrease. Okay, it is less than the gastric fluid, and because of that it will get float in the gastric fluid. Okay, and other thing, because of that swelling character, the total dosage form or the system will that much of enlarge that it will retain in the stomach, it will not get exit from the pylorus or pyloric sphincter. Okay, the second one is in hollow microsphere or microballoons. Okay, hollow microsphere or microballoons. So the polymer which is used in that, it is in polycarbonate or cellulose acetate or this calcium alginates. Okay, eudragite S. So these are the various polymers which is used to prepare those and uh, hollow microsphere or microballoons. Okay, now how we can prepare those microballoons or this microsphere? So one of the method is there, it is called that emulsion solvent diffusion method. Okay, emulsion solvent diffusion method. So two things is important, one is in solvent diffusion and the second one is an emulsion. So definitely there will be one two systems will be there. Okay, because of that there is an or you can say two phase will be there. These two phase will be form an emulsion, and the solvent will get diffused. So how it is possible? How to use that method to prepare that microballoons or microsphere? Okay, so a solution of a polymer and drug in ethanol methyl chloride is poured into an aqueous solution of PVA. PVA is a polymer. Okay, now one solution of a polymer and drug. So there isn't one solution, first solution, which is having the polymer and the drug. Okay, then there is an ethanol and methyl chloride is there. So mixture of this ethanol or methyl chloride in the ratio of suppose 1:1. So ethanol and methylene chloride, these two components will mix. Okay, then we'll pour it into the aqueous solution of PVA. So there's in two phases there. In one phase there is a solution. Which solution? Solution with having polymer and drug. Okay, the solution of a polymer, and the second one is that drug which is in present in that ethanol and methylene chloride. That one will pour it into an aqueous solution of PVA. Okay, so two systems are there. One system is having that ethanol and methylene chloride mixture with the drug, and second one is an polymer mixture. Okay, now if we'll combine this, the ethanol, as it will be miscible within water, so it will try to partition into that aqueous space, and remaining what is present? Remaining methylene chloride present, which is present in a droplet. So as we want to make it an emulsion, so one will be in the continuous phase and one will be in the disperse phase or the internal phase. Okay, so ethanol, as it will be miscible with the water, as we know that we have prepared a solution of an polymer. Okay, means aqueous solution. So the ethanol, it will try to partition, means it will go towards the aqueous system, so it is miscible with the aqueous system. So remaining what is present? Remaining present is the drug and the methylene chloride, that it will make a droplet. Okay, so the continuous phase is having an aqueous system. Okay, having one polymer, and the droplet is an methylene chloride droplet having the drug. Okay, now the polymer, they try to come into the surface of the droplet, methylene chloride droplet. Okay, then the methylene chloride, as it will be volatile, then it will try to evaporate, and then the drug will be present inside and the outer surface will be polymer. Okay, so whenever we make the two phase, one is an solution of an polymer and another one is an ethanol, methylene chloride and drug. So whenever you combine this, so ethanol, it will try to partition to the aqueous system, so it will mix with the aqueous system, and remaining the methylene chloride having the drug, it will make a droplet. So methylene chloride having the drug, it will make a droplet in the aqueous phase, which is having water and polymer. Now the polymer, it will try to go into the surface of each droplet. Now suppose one droplet, you can see that in that diagram, one droplet, it will covered by polymers. Okay, now the droplet is having methylene chloride and drug. Now methylene chloride, as it will volatile, it will get evaporated. So what will be present? Drug is present, but drug, it will not volatile, or it will not come outside, because the polymer already present in the surface. Okay, now as this methylene chloride will try to evaporate, there is a formation of an gas will be there, or you can say, as methylene chloride will be evaporated, there will be the droplet, it will make look like a balloon or a sphere, and those try to float in the gastric fluid. Okay, so you can see in the first diagram, the diagram formation of an emulsion, you can see the formation of the shell. The shell means the having that polymer. Okay, now the generation of gas phase, okay, that is in microballoons will form. Okay, so inside gas will form, or you can say that methylene chloride, it will definitely will be an evaporation will be there, methylene chloride will get evaporated. Okay, and that it will leads to the formation of an internal micro cavity. Okay, inside nothing will be there. Why? Because the methylene chloride will get evaporated, only drug will be present, and outside there will be a layer of polymer. So because of that, there is an microparticles or micro balloons will form, which will float in the gastric fluid. Okay, now third one is an alginate beads. So alginate beads, we how it will prepared. So normally we'll take two solution. One is a sodium alginate solution and another is a calcium chloride solution. Now the sodium alginate solution, whenever it will poured into the calcium chloride solution, it will make an beads. Okay, it will make in beads. How? By the precipitation of calcium alginate. Sodium alginate solution we pour into the calcium chloride. Now there is a formation of calcium alginate in the formation of in beads. That we can dry it, okay, and leading to a porous system. Once it will dry, some porous system will form, okay, which will maintain and floating system. So drug you can add in that sodium alginate, or drug you can add in the calcium chloride. So when there then bead will form, so one bead, the calcium alginate beads having drug molecules. So once will dry, it will make an porous system. Okay, once will get dry, the water will get evaporated and it will make an dry bits. Okay, small bits, a porous bits, which will float in the gastric fluid. Okay, the last one is the microporous membrane system. Okay, the microporous membrane system is the one of the system where there is an flotation chamber or floating chamber is there. Okay, and there is an membrane will be there. Okay, there is an, you can see in the diagram. So there is an microporous wall. Okay, microporous wall means a small pores will be there. Okay, and inside there will be a drug reservoir, and the total system is having one flotation chamber, and because of the flotation chamber, the total system will get float in the gastric fluid. Okay, so this system is based on the encapsulation of drug reservoir in the microporous compartment. You can see that this is an one reservoir type which is having one wall or polymeric wall which is having in micro size pores. Okay, so this, because of this floating chamber, there is an attachment of the floating chamber in that system. Because of the floating chamber, it will float in the gastric fluid. Okay, the once it will float for longer time, the gastric fluid, it will try to enter through the porous system. It will dissolve the water, and the drug it will release from the system. Okay, so these are microporous membrane system. So four systems are there in that non-effervescent. So we are not discussed here regarding any effervescent component or release of carbon dioxide. Okay, so there is a non-effervescent system without using any effervescent components. We are using various polymer normally which will get swelled. So in colloidal gel system, the swelling of the polymer which cause the uh, the swelling of the polymer, it will cause some you can say that balloon type, or you can say that air it will get entrapped into the system, and because of that the system will get float in the gastric fluid. Okay, any system will get swell, so the air it will be entrapped inside and the density will decrease. Okay, then it will get float in the gastric fluid. Even because of the size, it will not exit from the pyloric sphincter. Okay, then hollow microsphere, by an emulsion solvent diffusion method, we can make an microballoon or an hollow microsphere. Inside there will be an you can say that a porous system will be there. Okay, and third one, then alginate beads. There is a use of sodium alginate solution and solution of calcium chloride. There is an formation of calcium alginate beads. Okay, and the fourth one, the microporous system. the system which is having one polymeric membrane which is having the pores, and the system is having an flotation chamber. Because of that, the total system, it will get float in the gastric fluid, and the gastric fluid, it will slowly enter through the pores, and it will dissolve the drug, and the drug will release from the system. Okay, so these are the two types. Okay, so this is a completely floating system. One is an effervescent system, and second one is a non-effervescent system. So that's it. The next session we will discuss the remaining approaches of GRDDS.